Hey guys, this is just going to be a short little video review of all things particle motion. So if you didn't pick up a packet for this, there's one in a folder. It's in the same folder that should say particle motion worksheet PDF or something, and you can print one off. Otherwise, you should have picked one up either, what day is it today? Either Tuesday or Wednesday. So I'm going to go full screen on you here, and we're just going to talk about position, velocity, and acceleration. And obviously I'm not teaching it. When I do these reviews, they become short. I just need to review the basics and then you guys go practice them. For some reason it's not allowing me to turn the page. So just a second, I gotta go to my computer. So these problems are very common on the AP test, and it's pretty common that you would get an FRQ as well. So, you know, it's one of the top 9 categories of FRQs. I don't remember if last year they had a particle motion FRQ or not, but it's up there in terms of its frequency on an FRQ, and it's always all over the multiple choice. So we're just going to make sure you have the details down, and then you're going to go practice some multiple choice and FRQ. So what we usually have is an object is moving along some sort of a straight line. It's almost always the x-axis. I've seen a couple where they have them move vertically. Its position at any given time is called x of t. Sometimes our book actually even called it s of t. Sometimes College Board does, but either of these are pretty standard for position. This is the one they seem to gravitate towards. When we talk about average velocity, we talk about it as being your change in position over change in time. It's very common sense. For example, if you went 300 miles in, let's say, 6 hours, you would have traveled at a velocity of 50 miles per hour. Just change in position over change in time. If it were that easy, that'd be awesome, but that's not the level at which we do it, and you know that. Instantaneous velocity is the derivative of position. This is what's happening over a time interval. We take a derivative to figure out what's happening right now. So we say that velocity is the derivative of position. This is just for notation. Speed is the absolute value of velocity. It is never negative. The negative comes from direction. Speed is just magnitude. It's just how fast is it going, whether it's going forwards or backwards, we don't care. So we have it written as absolute value of velocity or absolute value of change in position over change in time. It's the same stuff. So this all becomes that SVA model that I told you about. You can call it X if you prefer for position, but when we are going this way, we take derivatives. When we are working this way, we integrate. So this is saying that we must integrate velocity to get to position. We must integrate acceleration to get to velocity. Total distance traveled is given by a formula, and we integrate the absolute value of the velocity, or basically we're integrating the speed to figure out total distance traveled. All right, so let's go to the next page here. We're going to talk about speed a little bit on this one. If velocity and acceleration have the same signs, it means velocity is positive, acceleration is positive, velocity is negative, acceleration is negative, then we say speed is increasing. Make sure you attach numbers to those on the AP exam. Don't just plug in on your calculator and say, oh, the velocity is 5 and the acceleration is 10, so I'm going to write speed increasing because both are positive. Make sure you say velocity at time 3 is 5, acceleration at times 3 is 10, therefore attach numbers to them just in case it's required. I've actually never read a particle motion one, to be honest. It's not one that I told you I always get stuck with graph analysis and separation of variables. Those are the two I tend to grade a lot. If velocity and acceleration have opposite signs, which means basically intuitively they're working against each other, like I am slowing down when I am going forward, like towards a stop sign, but my acceleration is negative. That makes me slow down and come to a stop. They're working against each other. So when we have these graphically, usually we'll see a graph of velocity. It's really important that you understand movement when you're given a graph of velocity. So velocity being positive means we are going forward. right? So right in here, my velocity is greater than 0, which would imply I'm either going to the right or up. It depends on what they tell you. If you're moving along the x-axis, I am moving to the right. If I'm moving along the y-axis, I'm moving to the left. But let's just say this just means I'm moving forward, or let's just for lack of a better, we're moving to the right here. Well, how we're moving is slower and slower and slower though, because maybe my velocity is 6 here, and then it's 5, and then it's 4. So although I'm continually going forward, I'm going forward slower. You would notice also here that my acceleration is negative. Acceleration is the derivative of velocity, and my slopes right here are negative. So we would say that from 0 to 2, that's slowing down. Also notice that when the graph is moving toward the x-axis, we're slowing down. Now, when I'm moving away from the x-axis, you'll notice over here, well, now my velocity is negative. What that means is I am going backwards. So my velocity is negative. It means I am moving left. Okay, so that would imply I'm moving left. How am I moving? Well, look at my speed here. This has a speed of 1 because speed is the absolute value of velocity. Sorry, my pens mean super slow. This has a speed of 2, and so my speed is increasing. But also take a look at my slopes are still negative here, so I have acceleration less than 0 also, so my speed is increasing. So graphically, it all falls into place as well. Moving towards the x-axis, my speed, absolute value of velocity, is decreasing. Moving away, my speed, or absolute value of velocity, is increasing, and the sign analysis works as well. So down below here, that's basically what this chart is saying. So in terms of movement, let's suppose this is little Bobby on his bike. Bobby is going to the right, slower and slower and slower and slower and slower. Right here, Bobby instantaneously has a velocity of 0, right? Now Bobby turns around and he's going back, but he's going back faster and faster and faster and faster and faster and faster and faster until he's right here. Now, if you want to think about like position, once he gets here, he's basically right back where he started. Now graphically, remember we integrate to go from velocity to position. Integration is the area under the curve, and you'll notice these triangles. This is a positive area, this is a negative area, but they're the same, and so we would be right back where we started. So we'd have 0 displacement. Bobby went forward, slower and slower and slower and slower and slower. Oh crap, gotta go back home. I forgot my book. Oh, now he's going faster, 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 faster. He's right back where he started. What's he doing right here? He is still going backwards. He is just going backwards slower. So he actually moved farther to the left. If you were to think about that in terms of position, we have way more area now below the curve. We are farther to the left. Right? That makes sense. That is when we are actually in this whole problem the farthest to the left. Now over here, we start to go forward again, and we're booking it faster, 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 just so you can get an idea how that goes. So on the next page, we're just going to talk about when you see certain words, what you should think. Initially is always at time 0. So this would be initial velocity, this would be initial acceleration, this would be initial position. At rest, we set our velocity equal to 0. If we have a calculator, we can graph it and calc 0. If we're given the position, we take the derivative and set it equal to 0. But when it asks for at rest, we want to know when is that velocity 0. At the origin is about position. It's, well, when is my position 0? Velocity being positive means we're moving right. If we're moving along the x-axis, it means we're moving up along the y-axis. Velocity being negative, again, means we're moving left. If we're moving horizontally, it means we're going down. So the sign of velocity tells you movement. So if you're ever asked when is the particle moving to the left, you need to figure out when the velocity is negative. These usually require sign charts, and you'll figure out where it's at rest first. So we find when is the velocity 0, and then if we made a sign chart and it went like this, it means the particle was going forward, stopped, went backwards, stopped, and continued going backwards. So if we were asked when the particle was moving to the left, we would say from 1 to infinity. Or you could say 1 to union 2 to infinity. That depends, because technically we have no movement instantaneously at 2. Average velocity, change in position over change in time. If you're given position, that's how you find average velocity. So if you're given a table that's charting the position over time and you're asked, what's my average velocity? You just do change in position. Maybe this is at 50 and it used to be at 20, so it moved 30 miles. Sorry, my smartboard's having an issue with the pens. And maybe this happened from 1 minute to 6 minutes. My average velocity would just be 30 miles per 5 hours. Again, you just change in position over change in time. 6 miles per hour is my average velocity when given position. Okay. Now, when I'm given the velocity, I take the average value of the velocity function. It's really important that you see that these are the same thing. So let me show you why. Our interval is usually a time interval. So I'm going to change the b minus a to a t2 minus t1. I'll integrate from t1 up to t2. So I'm just basically replacing these with time intervals. This is how we find the average velocity when we're given the velocity. It is actually also change in position over change in time because the antiderivative of velocity is position. So this is actually x of t evaluated from t1 to t2, which is equal to x of t2 minus x of t1, change in position, right? But I had this in front of it, and to avoid linkage, I should actually put that on all of these. But you'll notice that they both give me change in position over change in time. The same thing works with acceleration, so we'll talk about that in a little bit. We already talked about total distance traveled and speed. I think I want to add a displacement to this. So if you're asked for displacement, that's just change in position. If I was at 10, and now I'm at 80, I was displaced 70. But we want going backwards to count. So basically what we do, if I go forward 10 and back 3, I have traveled 13 miles. I need the absolute value of that 3. But if I just want to know my displacement, I want that negative to send me 3 back, and I will have been displaced 7. So we take the absolute value bars off for displacement. All right, so last thing, I'm at 12 minutes here. Sorry, I wanted it to be at 10, but last thing I want you to do is just really make sure you understand different uses or representations of some of these. So if I'm given a table charting time and it's charting velocity over time, and maybe this is time 2, I'm at 40, and let's go out here to time 5, I'm at, just make something up, 60, I don't really care. If I'm asked for average acceleration, think of this as being feet per second and time measured in seconds. To find average acceleration, so I'm going to write acceleration sub average, we would do change in velocity over change in time. So if I'm given a table of velocity, I just go, it was 20 feet per second per every 3, it won't write, sorry, seconds. And you'll notice if you do a unit analysis with this too, I'd get 20 feet per second, which is feet per second squared. However, if you are given the model for acceleration, so if it says a of t, my pen has completely stopped working, guys, so I'm just going to have to quit it there and we'll have to discuss the very last thing I wanted to discuss later. So you are to do the multiple choice, make sure you show work because I attached a key, so if you just circle A, C, C, D, that's on my key, so that doesn't tell me you really know what you're doing. Also, there's some FRQs, and the key is in Schoology in the folder that says Snow Day folder, I think. All right, have a good one. Bye.